This is a two-plane balancing cradle that is made by a place called Titan. And it's sold by a place in Australia called Dynex Hobby, and I'll put the link down in the description if you'd like to know more information about those folks. But what Dynex Hobby does is they're into drones and radio controlled helicopter platforms, and one of their, I guess, their focuses is balancing the props, the propellers and pulleys and flywheels, things that turn at a high speed and have to be balanced in order to eliminate vibrations to give a good stable camera platform. So anyway, that's the Dynex Hobby in Australia. And my friend James down at the Australian Television Archive, I have to give him a shout out here. He's on top of everything like this going on, and so if not for James, I wouldn't know a lot of things about stuff like this, pointing them out to me. So thank you, James, again. Anyway, this is a two-plane balancing cradle. So let's dig into it here and see what this thing is. Get all of our little pieces out and have a look at it. Now, these are machined aluminum, cast and machined, it appears to be, and fairly nice pieces. Here's we can focus in on that. Those are the folks that supply this little apparatus, Dynex Hobby. And check them out here on YouTube. They have several YouTube demonstration videos of some of their products. My goodness. Sure have a lot of pieces. suppose it might be a little bit easier if I were to lay this down and assemble it. Okay. That looks to be the same. There's no front or back, so I guess either way will work. One, two, three, 4, 5, 6, 7, 8. 1, 2, 5, 6, 1, 2, 4, 6, 1, 6, 7, 8. So the idea is for this carriage to be free floating. And of course we have 1, 2, 3, 4, 5, 6, 7, 8 roller bearings that facilitate that. So this would be one plane and this would be another plane, so two plane each end of the shaft. So let's continue on and assemble the other half of the carriage. Probably not doing this right, but that's never stopped me before. Okay, that looks right. So this piece would go there. And then we would need 4 more washers. So, by the way, these are Teflon locking nuts. They have a little Teflon ring up in the end. So when you tighten these down, the Teflon ring will keep them from backing off and getting loose. Because after all, balancing a rotating cart, you're going to have vibration. And of course, vibration will loosen up nuts and bolts if you don't have them locked down or secured. guess that would be a good way. Well, now for the small stuff. I'm going to screw these in, but I'm not going to tighten them down yet. These are the locking set screws to set the distance between the plane 1 and plane 2. Now, so as a, I guess a rough indication, we could set an assembled shaft on the cradle and set the distance. Now, what we don't have yet is we need some carrier bearings, 4, 2 here and 2 here, for this shaft to ride on. So this is just, will be a mock-up, a preliminary. Okay, outside to outside is 8 centimeters. So now we have our cradle assembled, our basic cradle in about the right dimensions needed to balance this drum and shaft. And so now what we need to add is the 4 bearings to carry the shaft. And we need to add a couple of accelerometers, one to each end of the cradle. And then we need to construct some sort of a pedestal to set this on, so we can add a DC variable speed motor in a belt to spin it. And well, let's see, after that is done, then we need to have an end stop for each end of the shaft to hold it in position to keep it from wandering from side to side and getting, damaging the drum against metal to metal. And last, we need to mount a sensor, a magnetic pickup, to sense the tach pulse on our tach disc. Where's our tach disc? Here we go. So that would be our sensor pickup right there in the tach disc. So if we mount our sensor somewhere, that will be our 0 degree indicator, or our index point. And the idea of balancing or dynamic balancing is, once you know the index, the starting point, as this turns, there's only one direction or two directions it can turn in, and that's forward to backwards, side to side. So if you know the starting point, when the heavy part gets around to this plane, then that's going to be the place that it swings the most, the heaviest part. So if we start at our 0, our tach pulse in this case, then we're going to know how many degrees from this starting point around this circle that we're out, or we are detecting the heaviest spot. And if you're looking at it on an oscilloscope trace, it's going to look like a sine wave, where you have more and more and more amplitude as the heaviest part gets to this side or to this side. Two plane is, well, you have, this side here is going to have its balance point, and this side here is going to have its balance point. And so you can balance both ends of the shaft through these balancing slugs on our tach disc and our head drum. Um, if it's very far out, you can lock down one plane and get the other plane in balance, and then lock it down, and then get this end in balance, and then go back with both planes free and touch it up. Now, this is a real-time situation here. You can do this with an oscilloscope, a dual trace, or preferably a four trace, so you can actually see the index pulse and the time between them. But if you don't have that, a dual trace with external trigger will work just the same. You would use the index as the external trigger input, and then our accelerometers, which we haven't talked about yet, would be the trace 1 and trace 2. So, trace 1 might be the drum side, and trace 2 would be the tack side. And so what you would see on the scope would be a couple of sinusoidal wave shapes, which are in coincidence with the maximum swing, or the point at which this is heavy or out of balance, measured from the index or the zero or starting point. And so if you lay this out on a scope screen, you got 0, 90, 180, 270, and back to 0, a sine wave. And so you can figure out the degree of the angle at which you need to add weight or take weight away. And of course, how we do that with balancing head drums is we screw the slugs in or out, more or less, to affect that offset in weight on each end. And so our next step would be to attach the accelerometers, one on each end of our carriage. And so this is going to detect the side-to-side motion, or the vibrations, caused by the motion. And that's going to create a small EMF, or a small voltage, or a small difference of potential that you can amplify and detect and observe on the oscilloscope trace. Now, that's a real-time way of doing this. If you were going to a display, an arithmetic or an algebraic type of a display, where you would have your two ends of your shaft displayed on a monitor, you would run it up to speed. The computer would take samples and then do some internal calculation, and it would put a dot or a line on each of your polar displays, which represent this end of the shaft and this end of the shaft. And that would tell you how much and the angle, and it would give you some figures as to how much weight you need to add or subtract at that point. That's not a real-time measurement. That's like a sample and hold, and then the computer calculates and figures out. Well, since we're not having to, you know, add or subtract weight in the sense that we're adding metal or we're drilling holes to take metal away, as you would like in a motor, like an electric motor shaft would have, or a heavy pulley, a mechanical type belt and pulley arrangement. That's already been done for us here in our case because we have balancing slugs that we can use to screw in or out to affect the weight, displacement, and the balance. So, well, you can do it that way, but it's kind of a long way, and there may be a little more guesswork in doing it that way. You know, and maybe get a little more complicated as to, you know, how it's doing it. But I always go for the simple stuff, and an oscilloscope is probably, you can't get much simpler than that. Doing something like this in real time. Well, so I guess we'll end part one here, and maybe in part two we'll attach the accelerometers and build us a motor pedestal and the roller bearings for the shaft to ride on, and build this thing. But there's always another way to do things, you know, and what we're interested in is we're interested in balancing a head drum. And you could build a cradle to put the whole head assembly on, and that'll work, certainly, but in my experience of doing this stuff the home-brewed way and not having access to a lot of fancy tools and things to work with, you sort of have to do this, you know, by the seat of your pants. What I have noticed when I try to dynamic balance the whole assembly as one piece is the most common thing I've run into is kind of a hit and miss thing. You have to start out at a low RPM because I have found that if you have a lot of unbalance, and usually that's the case, you know, when you mess with anything here, take away or add, even if it's a solder joint, a little more solder on one joint here than the other joint here, you know, that has a very big influence on the balance, you know, at the speeds we're working with. And what my experience has been many times, more than once, is if you introduce a lot of vibration into the rotary transformer, trying to balance the whole assembly as one piece. In the long run, you're damaging the rotary transformer. The clearances between the ferrite pieces in this transformer are very close, and it doesn't take, much vibration of this end shaft vibrating in here to knock those pieces together while they're turning, and that knocks little chips off the ferrite when that happens. And once that starts, now you have some pieces rolling around in there, which is the one thing you do not want. And that leads to more damage and more damage, and ultimately this thing, if it doesn't fail during the balancing process, it will fail at a later time, after you get it balanced and you're on the machine, doing transfer work. So just not having the necessary tools and test gear to do it as a whole, it's kind of led me to this. Let's just balance the one part that turns, and if we can get this part balanced, then the rest of this stuff doesn't move. So you can reassemble it, and then you can mount the head on a carriage and check it as a whole assembly. And so that minimizes any imbalance or any potential damage that you could cause, in the interim steps, trying to balance a head drum as one assembly. That's not the only way. This is not the only way, but this is a way that I found that will work, and you can do it without any fear of damaging any other components, such as the rotary transformer, in the process. Anyway, we'll continue on in our next video and do a little more assembly here and put this thing together and get it running. Now, this is not anything new as far as the idea of balancing the head drum apart from the rest of the head assembly. That goes back to the early days of 2-inch, back to the VR1000 era. And here is a head drum balancing apparatus that was used in the early days at Ampex to balance the Mark 1, 2, 3, and Mark 4 head drums. And so what it did was, this is mounted on a little spring carriage, and there's where you would mount the drum to be balanced on that little spindle. And there was a live shaft here, a motor shaft, and out here on the end you have a stepped pulley on the end of your shaft, and then down here the driven is also a stepped pulley, and you have a little belt, and the way you change the speeds is you change the belt position on the pulley to go faster or slower RPMs. And so this was an early balancing apparatus that Ampex used in the early days on back in the VR 1000 era. And so this is kind of a takeoff on this, in the sense that well, we're just balancing the part that moves. Maybe a little step further than this, in the sense that we're balancing not only the drum but the shaft and the tack disc. So we're doing the whole thing, and so that's kind of a little interesting piece of history, I guess, in the quad heads balancing, that maybe you haven't been aware of or have seen before. And my friend Bev Gooch gave this to me many years ago, and Bev retired from Ampex in the head engineering department. And if there was ever a guy to ask about anything to do with a video head or an audio head, Bev was, well, one of the guys, or maybe the guy. I think they're about all of them are gone now except Bev. He's maybe one of the last surviving people from this whole era. Well, I hope this little video has been informative and entertaining to you a little bit, and maybe made you aware of the possibilities of balancing a video head drum, and what's out in the world as far as some of the hardware that you can obtain very economically. I must say it's very affordable, and so I hope you can draw some ideas from my little project here that'll help you in your work. Thanks for watching.